Fluid dynamics. Fluid dynamics is a branch of fluid mechanics which is concerned with the study of fluid in motion. You see, the branch of fluid that studies motion of fluid without regarding the force which causes the motion is known as fluid kinematics. The dynamics of fluid flow is the study of fluid motion with the force that causes it to flow. So under fluid dynamics, we are considering the motion of fluid and with the force that causes that fluid to actually flow. Now, fluid dynamics actually is being analyzed using the Newton's second law of motion. First, let's look at the different types of energies. We can call them head of a liquid in motion. The first energy we are considering is potential energy, or you say potential head. This is the energy a liquid possesses due to its position above some reference line or datum line. It is denoted by Z. So you see, actually, potential energy, let me say that here, is simply mg. We say Z, we don't use H, we say Z. You see, if we divide this by mg, we are left with Z. Z is like height. So that's what we call a potential head. Head means height, actually. So that's what we use to represent the potential head, Z. Now, you can say kinetic energy of velocity head. This is energy a fluid possesses due to its velocity. It's given as v squared over 2g. How do we obtain this now? If potential energy is equal to kinetic energy, we have that mgh is equal to half mv squared. If you are dividing both sides by mg and divided by mg, you get h to be equal to v squared over 2g. That's how we got this formula. That means to say expressing kinetic energy in terms of head. We'll call it velocity head. Again, pressure energy or pressure head. Again, expressing pressure in terms of height. Okay, so the pressure energy is denoted with P, pressure over specific weight. And that's simply because, pressure is specific weight times height. So if you want to leave pressure in terms of height now, you have to divide both sides by specific weight. So pressure in terms of height is P over specific weight. So that's how we have this. So everything in terms of height. So these are the three energies we are considering for a fluid in motion. Now, what is total head? Total head is the sum of all these energy heads. Sum of the kinetic head, or you say velocity head, potential head, and pressure head. So total head is given as Z, potential head plus kinetic head plus pressure head. Let's take this question now. Example 1. In a pipe of 90 millimeter diameter, water is flowing with a mean velocity of 2 meters per second at a gauge pressure of 350 kilonewton per meter square. Determine the total head if the pipe is 8 meters above datum. Neglect friction. Okay? So now, let's evaluate this. First of all, what are the given parameters in this question? Well, we are given the diameter of the pipe. The diameter of the pipe is given as 90 millimeter. So we convert to meter divided by 1000. That will give us 0.09 meters. Again, we are given the velocity as 2 meters per second. And also, we are given the pressure head. The pressure, so gauge pressure, to be 350 kilonewton per meter square. which should be 350,000. Well, since the fluid is water, the specific weight of water is a constant, 9,810 Newton per meter square. Okay? And then again, so this is in Newton now, per meter square. Again, we have the pressure above the ground, which is 9, no, that's the height above the ground, 8 meter. So we can therefore say the total head H is given as Z plus V square over 2G plus P over W. So our H, total head, is given as our Z is 8 plus V, which is 2 square, over G. G is a constant, which is 9.81 meter per second square. So 2 times 9.81 plus P, which is the pressure, 350,000 over specific weight of water, 9810. So if we do this, we have our pressure head to be equal to 43.88 meters. So that's that for this question. Bernoulli equation. The Bernoulli equation states that for an ideal incompressible fluid, when the flow is steady and continuous, that the sum of kinetic energy, and potential energy is constant along a stream line. Okay, so the Bernoulli equation is giving us this actually. I didn't go about deriving the Bernoulli equation, but in deriving the Bernoulli equation, some assumptions are actually made. One is that the fluid is ideal and incompressible. Two, the flow is also steady and continuous. The flow is also along the streamline, that is, it is just one dimensional. Again, that the velocity is uniform over the section and is equal to the mean velocity. And then lastly, the only forces acting on the fluid are gravity forces and pressure forces alone. So that's that about that. Let's take an example under Bernoulli equation. All of this, the Bernoulli equation is just an extension of law of conservation of energy. Energy at entry just the same as energy at exit. Now let's take example 1 under this now. Example 1. Water is flowing through a pipe having diameters 20 cm and 10 cm at section 1 and 2 respectively. The rate of flow through the pipe is 35 liter per second. That's the discharge. Q is equal to 35 liter per seconds. That is just 35 over 1000. And that will give us 0.035 meter cube per seconds. The section 1 is 6 meter above datum and section 2 is 4 meter above datum. So it's going to look like this. Okay. Let's say this is the datum. Distance from here to here is 6 meters. And the distance from here to here is 4 meters. Okay. We have it again that this section here has a diameter. This is section 1. Section 1. That's a diameter of about 20 cm, not about. And this section here, section 2, this is 1, and this 2, has a diameter of 10 centimeter. Again, we are told that the pressure in section 1, P1, let's write that out now. P1 is given as 39.24 Newton per centimeter square. Well, I need to convert to meter square. You know, converting centimeter to meter is to divide by 100. Well, since centimeter is the denominator, I should be multiplying by 100. But this is not centimeter, this is centimeter square. So you multiply by 100 square. So 39.24 times 100 square. That will be 392400 Newton per meter square now. So that's the pressure at the section 1. What other parameter are we not given? Well, we know that the specific weight of water is a constant 9810 and G is gravity, which is 9.81 meter per second, Newton per meter cube. So now let's calculate the area of each section now. Area of section 1 will be given as, since the diameter is 20 cm, area of section 1 will be given as pi times the diameter of that section 1, 20 centimeter per meter, that will be 0.2 square over 4. And that will quickly give us 0.0314 meter squared. And area of section 2, likewise, pi times d squared now, which is 0.1 square over 4. And that will give us second section, the area is 0.00785 meter square. Okay, so we are asked to get the pressure at this second section. We're just going to use the Bernoulli equation now. Okay, to use the Bernoulli equation, we need to get the velocity at entry and exit. So let's quickly do that now. Since this charge is 0.035, Q is equal to A1 V1, or which is also A2 V2. So since we have our Q 0.035, which is equal to A1, we've gotten area 1 as 0.0314 times V1. We can say V1 is 0.035 over 0.0314. Simply, this will give us our V1 to be 1.114 meter per second. Likewise, 0.035 is equal to A2, and A2 is 0.00785 times V2. So we can say V2 is equal to 0.035 now, times divided by, 0.00785. So our V2 is equal to 4.456 meter per second. So since we've gotten that now, we can go ahead to use our Bernoulli equation now. P1 over W plus V square over 2G plus Z1 is equal to our Z, this is Z1, that's our Z2. So P2 over W again plus V2 square over 2G plus Z2. So we have our P1, which is pressure at entry. That's at 392400. 392400 divided by the specific weight 9810 plus our V1 square. That's 1.114 square over 2 times 9.81 plus our Z1, which is 6, is equal to our P2, which is what we're looking for, over W. The W is 9810 plus V2 square 4.456 square over 2g, 2 times 9.81, then plus the z2, and z2 is 4. So if we solve this now to get P2, our P2 will be equal to, simply, P2 will be equal to 40.2700 Newton per meter square. Using this equation and solve for V, you will get this answer. So that's that for this question.